That was probably the best one yet, actually. That was pretty good. Yeah, it was a good chorus. It was a good chorus. Alrighty, so today, Maya's not with us. She asked us to record, so we're recording. Today, we're going to be learning the last section of Chapter 6. We won't be finishing it today, though, so you don't have to worry about getting all the homework done tonight or anything like that. We're just starting it today. And we'll finish it tomorrow. Wednesday is going to be a day where you guys can get your homework questions for this section answered. And if the homework was decent enough or you're not quite sure what questions to ask, we're also just going to have general practice, like whiteboard style stuff, just so you guys can get all of the questions answered that you have. So section 6.6 is titled DeMoivre's Theorem and nth roots. That's DeMoivre's. It's French. That's how you say it. It's not DeMoivre's or anything like that. DeMoivre. Okay. We start this journey by talking about complex numbers, and we've talked about complex numbers in the past. Hopefully everybody knows what a complex number is, but just in case you don't, a complex number is any number that is a combination of a real portion and an imaginary portion. Imaginary does not mean we made it up. It's just what people eventually called it. Unfortunately, the imaginary unit I, its numeric value, because it is a number, its numeric value is square root of -1. But us being the simple creatures that we are, we do not have a better way of representing that value than with a symbol. Okay, it's like pi or e or square root 2. We just don't have a way to represent that value without symbols. So I is a number. And there's a reason why mathematicians get picky about your complex numbers being written in standard form. A plus bi form. Standard form means real comes first, imaginary part comes last. And you might have even heard it called the real component and the complex component. You guys ever heard it told like that? Said like that? No? Maybe? Well, it'd be great if you remembered that, because that's what it's supposed to be called, because we also just did some mathematics that involved things called components. Vectors. It's not an accident. Okay? Whoa, I wonder if they can hear that on the microphone. Who said that? Lizzie? She just says, I hate you. I hope you heard that. She clearly was talking to Alex and his cell phone, but I'm gonna email this video clip to Mrs. Mops and be like, hey, let's see what Lizzie's up to. Anyway. Stop taking videos of people's feet, you weirdo. Freaking weird, man. God. Anyway. It's never a dull moment. Never a dull moment. Mondays. But anyway, pay attention though. This is not easy. Pay attention. Okay, so complex numbers have two components, and I want you to start thinking about them as two-dimensional numbers. That's how this works. All the numbers that you know and love in the real number system exist on the x-axis, the real number line, but lines are one-dimensional. The imaginary numbers and complex numbers, they just pop off of it, above it or below it. So they do have a real part, and then they have an imaginary part. So we start thinking of them as coordinates in the imaginary plane. Our axes are the real axis and the imaginary axis, like you can see here. And you can treat the real component as the x value of your number, or x coordinate, and you could treat the b part, which is the number in front of I, as the y quote-unquote value or coordinate. It's almost like we're graphing a comma b in the complex plane. Yes, sir? Well, we treat them like vectors because we can do the same kind of math that we learned about vectors in them. I mean, what we did with vectors is we graphed them, added them, dot product, found angles between them, all that good stuff, their length, all that good stuff. We could do all of those things in the complex plane as well, because it acts like the Cartesian number system, x comma y. Only now it's a comma b. Okay. But we don't say comma, we say plus.
So the plus isn't like an equation.
No, it's like you grab Maya's paper again. Like this number, this is called a complex number. It has a real component and an imaginary component, but it is a number. It's a two-dimensional number. So if you had to imagine what that means, where it was, we go, okay, well, we've got the good old number line, right? And it's got the numbers that you know and love: -2, -1, 0, 1, 2, 3, and you're going, well, if this thing is a number, where does it fall? And I go, well, it falls on a vertical line that goes through this. And if I said plus 2, it's like it's up here actually, off of the real number line above it. And what we have here is the imaginary axis. So it's not that it's a vector, it is a quote unquote coordinate, if you want to think of it that way. Now, can I have vectors that go to there? Of course I can. And we will. Very, very soon, actually. So, okay. First things first, we got a skill that I'm not actually going to test you on, but I do want you to see it. Sebastian kind of ruined the fun already because he's already made the connection to vectors, but that's okay. Here we have complex number u, complex number v, and we're going to find a third complex number by adding them. Yeah, this is something you did in Algebra 2. Yeah. Adding complex numbers. So let's get to it. Yes, it is super easy. Now, when we have to do math with our complex numbers, they're typically wrapped around in parentheses. That way you could see this was a one structure, this was one structure. But when you add them, you legitimately just combine your like terms. So you combine the real things, 1 plus 2, and you combine the complex things, 3i minus I, gives me plus 2i. So there you have a third complex number. How about that? Add two complex numbers, the result is a complex number. This question asks us to plot u, v, and u plus v. Those 3 points together with the origin do form a quadrilateral because it's got 4 points. But what the book has asked us to figure out is if that quadrilateral is a parallelogram. Okay? Picture it drawn to scale as best as we can. And in the future, I think I'm just going to put a grid on here so it's much easier to do. But for now, we don't have a grid, so we're going to make do. There's my imaginary axis. Got our, well, real axis. Like so. We're going to plot point U in the coordinate plane, in the imaginary coordinate plane. 1, 2, 3. 1 plus 3i is right there. You can think of it as 3 imaginary units above the real number system. Okay, I is behaving as the quote-unquote y of a coordinate of an xy pair, but it's the real imaginary pair. Okay. What's next? Oh, this is u. And then v is 2 and then negative 1. So 2 on the real axis, negative 1 on the imaginary axis. That puts us down here. There's v. We found u plus v, so I'll do that one in blue. It is at 3, 2 in the imaginary plane. Puts us at the complex plane. There's u plus v. The question asks, do these 4 things along with the origin create a parallelogram? Well, let's see. We're going to do this by finding something that can work as a straight edge. Ah, yes. I'm going to draw that line, and then I'm going to draw this line. Actually, this one.
Are you going to do the distance formula?
I'm sorry? Oh, because it says that they form a quadrilateral, so it's just asked, yeah. It just wants to know, like, hey, if we threw those 4 points out there, does it make a parallelogram? That's all it's asking. And then the blue one is here.
Sorry, what?
Those are the 3. This was complex number u, complex number v, complex number u plus v. It wants to know if these 3 points plus this point make a quadrilateral.
So why did you connect that one to the origin?
I'm going to show you why in just a moment. That's interesting. That looks like it's parallel to the green line down here that complex number v gave us. And, well, if we did this, Hey, picture not drawn to scale, all right? I did the best I can. But let's see. What would make it a parallelogram? Well, yeah, if the opposite sides were parallel or if opposite sides were equal. Technically, the definition of a parallelogram is opposite sides parallel. But if we showed that the opposite sides were congruent, that would also kind of prove to us that it was a parallelogram. Geometry, baby. What? All right. So what are we going to do? I would say let's talk about parallel. Let's talk about opposite sides parallel. So let's look at the purple lines. I'm not colorblind. Purple lines. We're going to cheese this a little bit. We're just going to use slope. Okay. So if I start at the origin, the slope of the purple line is rise 3, run 1. So the slope of that purple line is 3 over 1. Do we agree to that? Well, let's see about this purple line. I have to go up 1, 2, 3, right 1. So the purple lines are parallel. Picture was almost scale, but they are parallel, or they should have been. And let's check the green ones. This original green line gave us slope of down 1, right 2. So we start here, down 1, right 2. I'll be darned. Opposite sides parallel. So what? Opposites. Whoa. What happened to my brain? I kind of like it. I know, right? Opposites. Opposing. Like, there's no way to fix that. That's supposed to say opposite sides. Yeah.
If we're gonna like, if we don't have like a graph or whatever to go,
Mm-hmm.
could we like, does like the 3 plus 2i work the same way as like an x plus y?
So
Like an x1 and a y1.
that's actually exactly what we did. Now, when did we do math like that recently, where we added the x's and then added the y's? Well, even before that, adding vectors. Remember when you add vectors, you just add the x's and add the y's?
Yeah.
And we call it head to tail or head tail method, something like that. If we treat them as vectors, then yeah, of course vector u plus vector v is the same thing as vector v plus vector u. Why would that matter? Order of operations tells us that order of mathematics, not mathematics, addition doesn't matter. Add in any direction you want. You're going to get the same thing. Creates a parallelogram. Of course it does. So if we're talking vectors, because now we're kind of there, and we see now that we can treat these things like vectors, one of the things that is very important about a vector is its length, right? Known as its magnitude. I could find the length of this purple line, right? But this wasn't actually a vector. It was a complex number. But since I can find the length, aka magnitude of that purple vector, that means I could actually find the distance that a complex number is away from the origin by doing the exact same math you did with vectors. It's literally the Pythagorean theorem once again. A squared plus b squared would have given you c squared, so if you take the square root of it, you get c. In this case, it's called the modulus of the complex number. Modulus of a complex number just means how far away from the origin is it. And you see here, this is a z. It is not bold because it's not a vector. But mathematicians use the letter z to denote complex numbers. So normally you wouldn't say u and v. You would say z1 and z2, meaning, hey, these are complex numbers. And I'm sure the paper just jumped in the video too because I actually don't know where it was when I paused it. But anyway, so we were just talking about the distance that a complex number is away from the origin, known as the modulus, and we said that they would be z1 and z2 and z3 and so on and so forth. So let us find the modulus of this complex number. You might have noticed here that it didn't have an I in it. That's because the I is being treated as a direction. It's telling you that you came up off of the real axis. The B is how far you came up off of the real axis. So we don't include the I here. The I doesn't hold value when we're plotting them and then finding their moduli. Okay? What's that? Yes, it does. I just said I is a number. It has value. Its value is the square root of -1. Now, just because our human brains are too pea-sized to comprehend what that means doesn't mean it doesn't hold value. It just means that we don't have a way of comprehending it. Let me ask you, can you draw the fourth dimension? Of course you can't. Can you even comprehend what that means? No, it's not. No, like actually mathematically the fourth dimension. No, exactly. Because we have human pea brains, but that doesn't mean it doesn't exist. So I is the way that we denote a direction and how far. It tells us you're popping up off the real number system, basically, into two-dimensional numbers. And by the way, you can't draw the fourth dimension because drawing happens on 2D surfaces, so it's impossible.
So why can't I draw 3D?
It's because you really can't.
Yeah, you really can't. You're drawing a 2D representation of a 3D surface. The first dimension is a line. That's why I said the x-axis is one-dimensional, and then the xi creates the second dimension. Yep. And 0 dimension is a point. Single point in space is 0 dimensions. Geometry, baby. All right, moduli, modulus. Let's do it. No, not magnitude. Mod z is square root of 3 squared plus -4 squared. I hope that everybody and their dog knows what that modulus equals without doing any math. 3, 4, 5. It's a 3, 4, 5 right triangle in the complex plane. Because that's going to be the square root of 9 plus 16. Root 25. So this is modulus of 5. This complex number is 5 units away from the origin in the complex plane. Ta-da! Yeah, I can show you what that means. No. Here, I'll just draw it. This is 3, -4 in the complex plane. So that puts me down in quadrant 4 of it. That's I. That's real. And we are here. I don't want to use blue again. We're here. And if I wanted to measure how far away from the origin this is, then we just grab that straight edge that I just lost. There it be. And we can measure it. And if we measure it, yeah, so we said, just like a vector. This would be considered the magnitude of that vector, if you wanted to call it that. It's 5 units away from that origin. That's how long that is. Because it's right 3, down 4, or you could have taken the straight shot of 5. Because it forms that 3, 4, 5 right triangle in the complex plane. Okay? Speaking of trigonometry, I love trig. Trig. You don't need to draw this, obviously. I'm just helping you out. So, what has been the progression of our trig skills thus far? So the first, hold on. So the first thing that we did way back in chapter 4 is we gave this point coordinates a comma b. X comma y, pardon my French. X comma y, right? And then we said, well, you know what? He's shaking his head no for. Oh. Then we said that this was distance x and distance y. And everybody was comfortable with that, right? And equation of circles, x squared plus y squared equals r squared. That's how we found out that this could be called r, right? Then we introduced thetas. And we learned some trigonometry. And what we said was, hey, did you know that the cosine of theta is x over r? So if I wanted to know what x was, I could just multiply both sides by r. Right? What do you mean, sure? I mean, that's what we did. R cosine theta. That's chapter 4. So this value down here is r cosine theta in the polar coordinate system, which is what we were doing on Friday. Polar coordinates. Sine of theta is y over r. Again, multiply both sides by r. You get y equals r sine theta. So from Cartesian to polar. And we treated those as vectors eventually, right? And we said that those were the components of our vector. So instead of saying r, we started saying mag v, trying to make it bold so it looks like a vector. But it meant the same thing, right? And we found that magnitude by squaring the x component and squaring the y component and adding them. What if I told you it's not xy anymore? Instead, it's real I, where the real number system does act as the x-axis, yes. And I throw a point on here, and I try to draw a straight line, so I'll cheat, use a tool. There you go. So instead of saying x, y, what we'll say is this is the point a plus bi. It has real component a and imaginary component b. This distance is now mod z, but that doesn't mean that trigonometry is gone, because you can still throw that theta on there. And we go, hey, did you know that cosine of theta is a over technically mod z, and sine of theta is b over mod z. Notice I'm not including I. That's because I is not holding value here, it's giving you directions. I told you come off the real number system. Anyway, you can multiply both these sides by mod z, and you would get that a is mod z cosine theta, b is mod z sine theta, and we have now used the polar coordinates and number system for complex numbers. But it's not new math. It's not. And you know what? I'll tell you what. I'll be really, really nice, and instead of saying mod z, we're going to make life real easy and agree that I could draw circles in the complex plane. Therefore, mod z would also be equal to r. Okay with that? So we can replace these with r's for easiness. What that means is this point, which is written in quote-unquote Cartesian style, can also be written in polar style, where instead of saying a, we say r cosine theta plus, and instead of saying b, we say r sine theta. But of course, the I is still part of it. I just put it after the R because it would be easier to say 2I than it would be to say I2, right? Yeah, it's all it is. It's just a substitution. But it's important that you see that this is how you can write every single complex number using trigonometry. That's all this table says. That's this. I just rebuilt this table for you, showing you where it comes from and showing you that it's not new. The only thing that we need to talk about is this word, the argument, because you might have noticed on my paper and then here, these are both the same theta. So we can call that theta the argument of the complex number, okay? Also, you could factor out an r if you wanted to, and it's still a lot to write, isn't it? I mean, look at all that junk. Well, mathematicians, you know, the lazy guys that they are, and gals, lazy guys and gals, I should say, don't want to write r times cosine theta plus I sine theta all this time. So instead, they write this. CIS theta, which stands for cosine plus I sine theta. Cosine theta plus I sine theta, and then of course multiply by r. What? Well, we don't say cis though, it's CIS. So they just say CIS. So r CIS theta. That is this, and I'll be using CIS theta instead of writing it out like this for time purposes and because, well, laziness. Cool beans? All right with that? All right, no one's freaking out, so we will move on. Here we have Cartesian coordinates for complex numbers. We're going to find polar versions of these complex numbers. When we can't do it by hand, we'll have to use a calculator. But we can do this one by hand. I'm sorry? The graphing calculators, you will not be able to use them on the test because it can do too much for you. This is the test. It's like, oh gosh, no. 1 negative root 3. That's going to be in quadrant 4. Picture not drawn to scale. The only thing we have to do is we have to make sure that our theta is a positive number, so it's actually out here. That's theta. But what we know is this side has a length of 1, and this side has a length of negative root 3. So what is the size of the radius? 2. Yeah, look, it's a special right triangle. It's a 1 root 3 special right triangle. So what is the size in degrees of the angle? Yeah, it's a 60-degree reference angle. 60 degrees in radians is pi over 3. So where is this angle then? The red angle. If this is pi over 3, what is the red angle?
5 pi over 3.
It's 5 pi over 3 because it's almost 2 pi, which would have been 6 pi over 3. So we know our theta is 5 pi over 3. And because it was a special right triangle, we know what the radius is. This Cartesian form of the complex number can be written polar form as z equals, and z just means this complex number, r sine theta plus ri sine theta, which is just too darn much to write over and over and over again when you're working with these things. And since, whoa, that's supposed to say cosine. Oh my golly. There we go. Not sure what just happened. Small stroke, sorry. R cosine theta plus 2i sine theta. Anyway, we would short. What? That's r. That's the r cosine theta plus ri sine theta. Like this. You don't. So, okay, hold on. Too many questions. So you cannot put CIS in the calculator. You would have to do it like this. And it doesn't understand the I. You know, you can't. I mean, well, it kind of does. But you have to tell the calculator more, have to be a little bit smarter about it. But there isn't a way to shorthand it in the calculator. And the only reason why theta was positive is because they said it was. It could have been negative, yeah. Isn't it so much prettier to write? It's just so much easier. 2 CIS 5 pi over 3. All right. What's that? It's right there, S. The C stands for cosine theta and the S stands for sine theta. They have the same theta. It's 5 pi over 3. So we just shorthand it. This isn't a command, it's shorthand. It means cosine plus I sine. Cis. 2 cis 5 pi over 3. Okay, this one. We're not going to be able to figure out theta by hand. We will have to use a calculator because once again, we're going to have a 3, 4, 5 right triangle in our hands. That's not one of the special ones that we've memorized as far as angles are concerned. So trig will be our friend there. But since they're both negative, I'm going to draw myself a triangle in quadrant 3. Theta is out here, all the way to there, like that. What's the modulus of this complex number? It's 5. It's a 3, 4, 5 right triangle. So we already know r, it's 5. We just need to know theta. Well, I could do lots of trig in this triangle. And then I'd need to use inverse trig to capture that angle. The problem is no inverse trig functions are going to give us a result in quadrant 3. So what do we do? Well, pick one, and then just know how to reflect it to the appropriate quadrant. I am going to use tangent. I think it's the easiest, and let me show you why. Tangent of theta is -4 over -3, so positive 4/3. And when we use tangent inverse, we're going to get a result in quadrant 1. Make sure, I want to do this in degrees, so you make sure you're in degree mode. You go second tangent, 4 divided by 3, close it up. There we go. It's about 53.1 degrees.
Then you just add 180.
Here's what we just found. The negative radius version of that thing. The negative radius version of it and the positive radius version of it are exactly 180 degrees away from each other. So we just take the result we got and add 180 degrees. To 33.1 degrees. We know r, we know theta, we can write it in polar form. There. And again, I prefer CIS. It's just shorter. There's less to write. You know, you can do it a little bit faster. 5 cosine I sine of 233.1 degrees. And if it helps you, you could do this. That way it reminds you that that is the argument of two different trigonometries. But that's it. Not bad, is it? It's the same math we were... Wait, it's not even an equation. This is a number. This is the same number as this. It's just in polar form. It's just written in polar form using trigonometry because a lot of very nice things happen in polar form, especially for complex numbers. They make life very, very easy. For example, let me remind you of something that you did in Algebra 2. In Algebra 2, we could ask you to multiply two complex numbers. So let me make one up. How about 1 plus 2i? And, I don't know, I don't really care, 2 minus I. I could ask you to multiply those back in Algebra 2, and here's what you would have done. You would have FOILed, right? The results would have been 2, let's see, minus I plus 4I minus 2I squared. So 2 plus 3I, and since I is the square root of -1, I squared equals -1. So you ended up with 4 plus 3i. So yeah, multiplying two complex numbers gave us back a complex number. Well, if you can multiply in Cartesian, why shouldn't you be allowed to multiply in polar? So let's say, for funsies, that z1 is, let's keep the numbers small. How about 2 cosine, not cosine, 2 CIS, sorry. 2 CIS of 40 degrees. And I tell you that z2 is 3 CIS of 20 degrees. Now, neither of those numbers is a special right angle for, or is a special right triangle for us, so we would have to use a calculator, right? Wrong. That's only if you want the Cartesian form of the number. See, in polar, it's going to remain in degrees. Let's go ahead and multiply that out using good old-fashioned foiling skills. So that's going to give us 2 cosine 40 degrees plus 2I sine of 40 degrees. And we're going to FOIL that with 3 cosine of 20 degrees plus 3I sine of 20 degrees. This is brutal. Watch this. So we're going to do that multiplication and that multiplication. I'll do those in purple. So it's going to give me 6 cosine 40 cosine 20. And then here to here, 6I cosine 40 sine 20. Then here to here, that gives me 6I sine 40 cosine 20. And then the last one from here to here, 6I squared sine 40 sine 20. But I squared is -1, right? Okay. So if you don't mind, I'm just going to write this in a different order since this is real now. Hey, pay attention back there. No, you're not. You're talking to Alex.
I literally asked him. I just said I do mine.
This guy. It's going to give us 6 cos 40 cos 20 minus 6 sine 40 cos 20. Ah, and we're hearing people across the room realize what's happening here. Then these 6I cosine 40 sine 20. Hold on. Plus 6I sine 40 cosine 20. Did I make a mistake?
Yeah, it's
What?
in the -6 sine 40, it's sine 20.
What did I write? Oh, sine, not cosine? Oh, sorry. There. I'm showing you why. Stop asking why we do this. I swear to God, I'm going to come back there and I'm going to just shake the fire out of him. He is upsetting me today. Factor out the 6. Pretend you don't see the 6's. What do you see? Cos, cos, sine, sine. Ah, yeah, you get trig stuff. Cos, cos, sine, sine. With a minus in between. Oh, that's cosine of A plus B. So this is 6 cosine of 40 plus 20.
That's what's up. I forgot about that.
And you know what? Check this out. If you pull 6I out of this, it goes cos, sine, sine, cos.
That's cosine. No, sine.
That's the sine addition formula. Which means if you this gives you, let's pull these two 6, let's pull 6 out. And if you pull 6 out, it gives you cosine of 60 degrees plus I sine of 60 degrees. Holy cow. That is literally 6 CIS of 40 plus 20. It's like we just discovered the formula that is right here in these boxes. That's why this works. Because it uses the trig sum and difference identities. The trig sum identity results in this formula in polar coordinates. Even prettier is R1, R2 CIS. Theta 1 plus theta 2. Look, my two radii were 2 and 3. R1, R2, CIS, theta 1 plus theta 2. And if you understand why the multiplication formula gives you a product on the front and then a sum on the inside, it should make a lot of sense why the quotient formula gives us a quotient of the radii and just theta 1 minus theta 2 on the inside. And yes, you do need to know these formulas for your test. I'm not giving you a reference sheet. Oh, world's tiniest violin. But it's not new math. It just looks like it. You just saw me use our old skills to build this, and I could do the exact same thing for that if I wanted to. How useful it is having those trig skills from the last couple chapters. Oh, by the way, I don't know if you caught that, but 40 degrees, which is not a special triangle, and 20 degrees, which is not a special triangle, the way I set this up, you could evaluate this by hand and tell me what the product of these two ugly complex numbers would be in Cartesian number system, and you could do it without a calculator because 60 degrees is one of the special ones. How about that? So much fun.